This physics review video is from Unit 6, Energy. The topic is work and energy. Work is the change in energy levels. If I start with 5 units of energy and I go up to 13 units of energy, that's a change of 8. The work done on that object was 8 units of energy. Work is measured in joules. Energy is the ability to do work. So if something has a lot of energy, it's able to do a lot of work. It's also measured in joules. Because they're measured in the same thing, they are able to be added and subtracted. In order to find out how much work is done on an object or by an object, we need to know 2 things. One is, how hard is something pushing on or pulling on that object? We call that force. So that's one factor that influences the work done on an object or by an object. The other one is, well, how much distance are we applying that force for? And we call that displacement. It's very important to remember, back from Unit 1 or Unit 2, that distance and displacement are not the same thing. Displacement is the distance from beginning to end in a straight line. So, here are some examples of how I can do work. If I apply a force in this direction on this object, and it goes this direction, work is done. Yay. However, if I apply my force in a different direction, let's say I apply my force upwards, I'm holding an object. So let's imagine I'm holding a book. So my force that I'm applying to that book is upwards, and I walk across the room, my displacement is that way. In this case, there is no work done. The reason there is no work done is because my force and displacement vectors are at 90 degrees. They're perpendicular to each other. So no work is done in this case. So force and displacement must be in the same direction. There are 3 types of energy that we're going to talk about in this video. The first is potential energy. This is stored energy. The one we're going to deal with most is energy that is stored gravitationally, or gravitational potential energy. The next type of energy is called kinetic energy. That's energy of motion. Any object that is moving has kinetic energy. And the third is called thermal energy. This is the energy we actually experience the most, but it's actually the one we know or we use the least. It's energy based on the temperature of an object. It's often lost. So if, for instance, you rub your hands against each other a lot, that energy that's kinetic because you're moving your hands, your hands are moving, it's going to build up a lot of heat. That heat is called thermal energy. That thermal energy is then going to be lost. It goes out to the air. The air heats up, but that energy then eventually leaves, and the Earth is actually losing energy through thermal radiation to space all the time. Energy equations. This is gravitational potential energy. That's why that little G is right there. Gravitational potential energy. 3 things impact how much energy something can have gravitationally. The first is, how big is it? If it's a very big object, it's going to be much harder for me to do work on it. The second one is gravity. How strong is the gravity where you're at? On Earth, we use 9.8 meters per second squared. And last but not least, to figure out how much energy something has, is how much work does it take to get something up there? And if up there, lifting it up is a lot higher, it's going to take more work. So we also need to know the height above whatever reference point you're using. Those are the 3 factors that we use for gravitational potential energy. It can be shortened by writing it like this, mgh. Okay, the second type that we have an equation for is kinetic energy. two things affect how much kinetic energy something has. The first is mass, again, how big it is. So this is why a freight train will do more damage in an accident than a Mini Cooper, because it's got significantly more mass. The second factor is, well, how fast is it going? If it's going very, very fast, it means it has a lot of motion, which means it has a lot more energy. And velocity, if you'll notice, is actually squared. That's because velocity is more impactful than mass, finding out how much kinetic energy something is. So something can actually do more work if it's smaller, but if it's going much faster. An example of this would be a baseball thrown at 100 miles an hour will do more do more work than a book that's going 2 miles per hour, even though the book's bigger than the ball. The ball is traveling much, much faster, so it'll have more energy. Okay, so here's an example problem for gravitational potential energy. I've got a mass, 2 kilograms, that's my mass. My height is 6 meters, that's h. And g, again, is 9.8 meters per second squared. So in order to find the gravitational potential energy, I use mgh. My mass is 2 times 9.8 times my height of 6. When I multiply this through, I get an answer of 117.6 joules. We can shorten joules with just J if you'd like. So 117.6 joules. That's how much work this ball will be able to do to the ground when it hits. It will do 117.6 joules of work. Also, it would take that much energy to raise it up to this point. So if I had a ball that was down here, it has 0 joules of energy. To get it up here, to lift it up there, it would also take 117.6 joules of work to get it to that much energy. An example of kinetic energy. Here I've got a ball that's moving. Its mass is 2 kilograms still. Its velocity is 6 meters per second. My kinetic energy is equal to 1/2 mv squared. In this case, my mass is 2 kilograms. My velocity is 6 meters per second. And that whole value is squared. You'll notice that 1/2 and 2 cancel out. So I get 6 squared, or 36 joules. In this case, that's how much energy it has, but it's also how much work was done to it. If the ball was over here at rest at 0 meters per second, it has 0 joules of energy. In order to get it to this situation, I would have to add 36 joules of energy to get it up to that speed. These are examples of different types of energy dealing with work.